Oh, there's a delay.
Oh, oh,
Do you see it
we're
now?
live?
Do you guys see it?
Yeah.
Oh, we're live now?
Hey, everyone.
Hi,
Oh,
sorry
there's a
about this.
delay.
Oh, wow.
Oh,
Okay. I think that there's just like a few minutes or like few seconds delay, so it's like confusing. But you guys can see this, right? Just like thumbs up.
yeah, we should be good.
Okay, fire. Yeah. Hi guys. Welcome to HackMIT 2025 puzzle walkthrough. Feel free to like say hi or like put any questions that you get like while watching the slides in like the live chat because we're monitoring that. Yeah. Anyways, we're the HackMIT dev team and also some alumni. So yeah. Also, if you type in go/puzzle-walkthroughs, actually, can one of you guys put that in the like YouTube chat right now? You should be able to follow along with our slideshow. Yeah, and I think we can maybe get started now. Okay. So, what is puzzle? Basically, if you guys have attended Hack or just followed along with us in these past years, we do like a CTF style admission challenge every single year. So we have like 5 or 6 puzzles, and then the people who score on the leaderboard or like the top 50 scores get auto admission into our hackathon, which is September 13th. So hope to see you guys there. And this is just a link to our previous walkthrough and the slideshows. And here is the link to our command center. It was based off Cool Math Games this year. Yeah, feel free to like drop any questions, by the way. And then my lovely teammates will let me know. Okay, overall stats. So this year, 920 people created a account, and here are the rest of the stats. Reminder that these slides will be like sent out, so yeah, feel free to look at these later. And yeah. Okay, so every year we have a way to get to our command center, which is our cool hack games, from our like actual website at hackmit.org. And so this year we added a new FAQ saying, where can I find the admissions puzzle? And the keyword here was games. And we also have a sign. Here's a screenshot that says arcane. And if you clicked on this sign, this secret code, this like popped up, and that's just like the start date of our hackathon, which is 90913. Yeah. And then it should redirect you to here. You could also just like look at like the network stuff. But yeah, this is the official way. Shout out to marketing for very cute designs. Okay, let's get started. So this is one of our first puzzles, also the one with the most solves. This is triple tile. And if you guys are familiar with the actual triple tile game on like the App Store, it's basically that, but with like a Morse code twist. So you need to match groups of 3 tiles without overflowing the tray. And each of these 10 buildings has like windows that like if you solve enough, if you match enough, they start flashing in Morse code. And one interesting thing is that they unlock in order, like this building with one window unlocks first, then this is second. So that tells you like it eventually spells out a word. Yeah. So how to solve this? So there's multiple ways to get the flag. The first one is actually like solving it, like getting enough matches and finding the full Morse code and then submitting the flag with the flag button. This is the flag, by the way. Or you can use the export puzzle button and write a script to automate solving the triple tile game. And prior to the patch, same for Papa Cipheria, you could also have found the code using API endpoint. So if you guys did that, good job. Good for you guys. And then you should be able to see this hash. Everyone has their own, and you can submit it to our command center. Are there any questions so far, or are we good? Okay, nice. Um, for the second puzzle is Papa Cipheria. So this is based off like the Papa's Freezeria, like Pizzeria, the franchise Uncool math games, which I played a lot of when I was younger. And yeah, basically it was split into two phases. And the challenge is just to like solve a cipher because instead of like ordering pizza, they're ordering ciphers now. And we provided some hints to tell you what type of cipher they are. And each phase, there's two phases, requires you to think of like all your answers to the ciphers. So, like for example, um, one of the ciphers was like, here, have fun hacking this one, and here hack was the key, and it was a Visioneer cipher. And that would decrypt to don't be still like paper, which is stationary. And all of the solutions to the ciphers are at our Go link. So Go links are something we do to make it a lot easier so you guys don't have to type in like a very long URL. If you type in go.hackmit.org/pp-sol, SOL, that should work. I think we can definitely like put this in the chat, or you guys can just like follow along on the slideshow and click this link. That should also work. Cool. I'm gonna hand this off to Adam and Evan, who made chess.
Yeah, hi. So, I made chess along with Adam, and
Hey.
so when you see the front page, there's not much to this puzzle, and this puzzle is like not interactive at all, like compared to the previous puzzles. Basically, all you have is the title, which says a chessboard is worth 64 squares. This is a reference to an image is worth 16 by 16 words, if you know what that is. But anyways, the important part of this title is just the 64, which I guess everyone knows, but it's just here to emphasize 64, which we'll get to later. And then you have the image of the chessboard along with the caption, how do we get there? And this image doesn't have it, but later we added the hint, which said A equals 0. And at the bottom, you just have this jumbled ciphertext, which might look like, I mean, if you've seen base64 encoded images before, it might look familiar. Yeah, so the first part to solving this is, since there's not much to do, I think a general thing with like puzzle hunts and things is if there's nothing on the page and there's just images, it's likely those images will have some metadata. And so you can download the image and you can check the metadata. There's like websites to do this, or you can also just check it yourself. And there's actually a PGN field in the PNG metadata. I guess originally when we were discussing puzzle ideas, this was like a we thought it was funny that PGN, like you just rearrange it. So but yeah, there's a PGN there, and it seems to be the chess game. And the following slides will show what the state is, but we have around 184 moves here, but it's not exactly complete.
All right. So now we can either use the hint or kind of use the title of the puzzle, which is an image is worth, or chessboard is worth 64 squares, and kind of try to map the game to a base 64 sequence. So we can do that with this game since we have the move order. Each half move ends on a square. We're careful to have our game not include a castle. So since every move ends on a square, we can decode every move into a base 64 digit. And now we have two base 64 streams, the game and the ciphertext. So what do you do then? Well, you can XOR them, which is a common thing to do when you have two binary sequences or base 64 or whatever. Another thing that you might note is that the game is kind of still a partial game, and the PGN move length is less than the ciphertext length. So it kind of hints that you're going to want to solve the entire game or figure out the entire chess game, and then you'll be able to XOR the entire chess game with the entire ciphertext. But anyway, if you decode what you have, you'll receive this message. It says complete a full Wikipedia GIF Knight's Tour. If a white piece must get out of the way of the tour, move it forward. The black king always prefers moving to squares that are the smallest possible value, but will never capture a piece. Finish with a mate in three. So it kind of um, tells you exactly what to do. If you look up Knight's Tour on Wikipedia, then the first image or the first GIF that you see is like just like an animation of an example of a Knight's Tour. And that's kind of exactly what you need to apply. So yeah, here we have that. On the bottom right is the Knight's Tour if you search Wikipedia for Knight's Tour. And this is kind of a tedious part that some people on the Discord were complaining about. But anyway, once you do this, you'll have finished the game, and now you can XOR the full PGN with the full ciphertext. And when you do that, the last part says, brilliant move. The flag is as follows, and then your flag. So I hope you enjoyed this puzzle.
All right, so moving on to Jailbreak. When you visit the page, you have this very short bash script in the code block, and you have a link to download the deployment setup. And this bash script only takes two inputs, two lines of text. And it looks like it just assigns a variable and then does nothing. So how can we exploit this? Well, first of all, I want to shout out where this challenge was inspired from. It's this challenge on pwn.college. It's a great site for learning CTF and binary exploitation. Y'all should check it out. But the first thing you will notice about this script is it uses this built-in command declare-n. And what that does is it creates a variable or pointer variable, which allows you to assign a variable indirectly. So that's what allows the script to take in the name of a variable that you want to set. And then when it assigns that pointer variable, it'll actually be assigning to whatever variable name the user put in. So with that out of the way, we can start thinking about different attack ideas. So you might think, okay, well, maybe we could inject into the path or other similar path-like variables, but there's no commands after the assignment that you could hijack the path to. And you might look at some of the bash built-in variables, think, okay, some of these bash underscore variables might have some exploitation potential, but that filter on the variable name, it only allows letters and numbers. So since all those bash variables have that underscore in them, you can't access them. So uh, what you might do a bunch of research after this, but one of the canonical resources about bash exploitation, I guess you could call it, is this wiki page called Bash Pitfalls. And it has like 50 different sections on different types of bugs you can make using bash. And number 7 here, the heading doesn't look anything like our script. It's talking about these double brackets, which are often used in the if command to test for a condition, but it goes on to talk about this thing called arithmetic expressions. Now, that mode is activated by using those double parentheses, and you can use it to do very basic math commands. This is a bash specific feature. It's not present in other POSIX shells, and that math environment, if you let untrusted input be evaluated in that math environment, you can very easily get command injection. And while if in the script it doesn't look like that's happening, what can actually happen is that if you try to assign to an arithmetic variable, this arithmetic expression will implicitly happen. So if we look at the deployment setup, we see that the flag is written to this file temp flag, and the challenge, the bash script can read it. So if we were able to enter this arithmetic expression environment and refer to any variable, it can be a non-existent variable, in this case, x, and then you try to index that variable, you can run a command that will read that file. So, and then the output of that command will show up in an error message that bash outputs. So the solution would be to write to any variable that causes arithmetic expression. So I used opt-in. I've seen other people use seconds, random. There's probably others that I'm forgetting, but those are the three that I know to work. And then a payload sort of similar to the one on the slide with an array indexed by a command substitution that cats the flag. All right, so moving on to lemonade stand. So the first thing that you would notice when you open the website is there's these interactive features, but they all seem to be sending commands over this WebSocket stream. So here's a view of the network tab in your browser developer tools, and you see that it's connecting to this path/ws for WebSocket, and it's sending some text-based commands. It looks like first a user ID, and then a few commands where the first word is the command name, and then there's a few space-separated arguments to that command. So creating a stand, setting the recipe, simulating it. So this is interesting. So next, if you download the deployment setup, you can start looking at how this all works. So there's this Docker file called dockerfile.backend, and how that's exposed to the WebSocket isn't really important, but you just need to know that the input and output of this Docker container is connected to the WebSocket. So there's this hint in the Docker file. It says, I heard older libc versions have faster memory allocation. So there's already a hint about memory allocation and about paying attention to the libc version, maybe relating to this next line in the Docker file. So then after that, it copies this file lemonade_stand, and then it copies an entry point script. So that would be our next files to look at. So we see in the entry point script, it's very similar to Jailbreak. The flag is written to a file in the temp folder, temp flag. And then if we check out this lemonade stand file, we see that it's a 64-bit ELF Linux binary, dynamically linked. So our next step would be to look at that binary. So I'm using checksec, which is a command from the PwnTools Python package, and it prints out some information about the protections or mitigations that were enabled when this binary was compiled. A few of these aren't relevant, but the relevant ones are no stripping, which means that all of the original function names and symbol names in the binary, not in any libraries that it imports, but in this binary, all of those names are going to be preserved as they were in the source code. So that'll make reverse engineering a bit easier. And then no position and independent execution or pi. This means that those functions and symbols in the binary, they're always going to have the same address, starting with that 0x4 and then a bunch of zeros base address. So all those functions and data will be relative to that constant base address. And so we don't need to be leaking addresses to find random values. So that'll make our exploit easier. And then we check the dependencies. We see that it depends on the math library and the C library, so nothing out of the ordinary there. So next you can open it up in your favorite reverse engineering tool like IDA, Binary Ninja, or Ghidra. In this case is what I used. And you should be able to find the main function pretty easily with the symbols. And in the main function, you can look at the C decompilation. When you open Gitra, it should prompt you to analyze the binary. If you say yes, leave all the default options, just check decompiler parameter ID. That gives you a bit of a nicer C decompilation. And then in that main function, you should see a big main loop where we read a command every iteration after that enter command prompt. And then we compare the command received to various supported commands. So next, let me just go over a quick crash course in the scanf function. So man3 scanf, that's the command you would do on the command line to open up the man page. You can also just type that into Google and it'll come up with some online versions of the man pages. And this function scanf, it's basically like printf, but in reverse, where printf, you're using format specifiers to convert variables and print them out. With scanf, you're using these format specifiers to read input and read it into the variables that you pass into scanf, which would be local variables. So the relevant one for this binary is %s, which will read a string, and that string has to be a single field in the input, which is read from stand-in. And importantly, it cannot have any white space characters, which are spaces, tabs, new lines, or null bytes. So that's 5 or 6 different bytes that you can't use with scanf. Scanf will not pass them through. It'll interpret it as the end of that word, and it will just write the terminating null byte for that string instead. And then the number after the percent is the maximum field width. So that's the maximum number of bytes that you'll be able to read in that scanf call. So that limits your potential to do overflows or anything like that. So next we're going to reverse engineer a few of these different commands that the binary supports. So the first one being stand create. And stand create takes an index, which I forgot on the slide, but it should be create index and then the length of the name and then the name. And we see a length, we might think, oh, can we overflow that? Well, it's actually allocating on the heap a chunk with exactly the size you specify +1 for the terminating null byte. And then it's dynamically generating a scanf specifier. So those first 2% signs in that SN printf call, those are going to print out a literal percent. And print out is figurative here because it's all going into that character buffer format that's on the stack because this is SN printf and not normal printf. So it'll first add that literal percent and then %d will print out the decimal version of size and then an s. So then that'll create percent size s, where s is the size of the chunk that you wanted. So that prevents us from overflowing the heap chunk. And then we read in that string using that format specifier into the name, which is returned from malloc. So we can allocate heap chunks of an arbitrary size, but we're limited to that size. We can't overflow it. And we can only write bytes that scanf supports. Okay, stand delete is the next command. Um, it also takes an index and it calls free on that index if it's not a null pointer. And so the important thing to notice here is that it doesn't write it doesn't clear out that pointer. That pointer is still going to be there in names index. It's not going to be set to null. So that means that you can call free as many times as you want. I mean, provided that the binary doesn't crash internally in the free function, of course. Um, but that is already a vulnerability. And then that memset just sets a bunch the numbers inside the recipe struct to 0. So that's not too important. And so that double free is what it's called, will be an important primitive for us later. Okay, stand rename. So it scans in an index the same way as the other commands, and then it uses this function malloc usable size on the name pointer. And this is a function provided by the allocator that will return how the usable size of that chunk so that we don't overflow into the next chunk. But it also means that the program isn't internally keeping track of the size of these names. It's just relying on the heap's own accounting. So maybe we could trick that potentially, but still no overflow here. But it reruns that same dynamically generated scanf format code and reads in the stand name. And so that allows us to edit the content of our heap chunks. And then combined with that last command where free doesn't delete the pointer, that means we can call stand rename on freed chunks as well. So we can edit freed chunks and potentially corrupt the metadata inside. So that'll be important. And then the final important thing from the reverse engineering is the win function. So there's this command send flag, takes a password, and after a few checks, it will read and print out the flag file. So this makes exploitation way easier. We don't have to reuse code from within the binary. We can just directly try and get this send flag command to work. And then if we can pass all the checks, that means that we can get our flag. So what are these checks? So the first one is this global G debug control, the 4 bytes at that location. Mode is 0 offset, so just at the address of G debug control. Those first 4 bytes have to be set to 0 because it does an integer compare 4 bytes. And so that's interesting because, like we said, the null byte is one of those bytes that scanf will not be able to write for us. So we'll have to get around that. And then we have to include a password as an argument to the command, and that has to match the string stored at debug password offset of this gdebug control. And if we dig a little bit deeper into the binary, this is a bit more advanced reverse engineering. You could also verify this using a debugger, but if you read that password in the debugger each time, you'll notice that it's a random ASCII string in using only lowercase letters every time. So you can't just predict that password. So we need to somehow override that password to a value that we do know so that we can read the flag file. So other commands that are not too important, set recipe, it just sets a few numbers on the stack. Copy recipe, same thing, except it's copying instead of reading from the arguments. And then simulate, the only important thing it does is that it prints out bytes of a name up until a null byte because it's %s. So you can potentially read the values inside of heap chunks up to a null byte. So that could potentially give us an arbitrary read if we were to control what those heap chunks point to. Okay, so given these primitives, allocate, free, edit, and read, that's more than enough to do basically any heap attack that we want but that only relies on metadata inside of the chunk. So because we don't have position independent execution, we know the address of gdebug control. So we know exactly where we need to write. Um, and if we have an arbitrary write gadget, we can use that known address and write the mode and password. And then we'll be able to call that send flag command. But we must be able to write a null byte for the mode, and all hints point to heap exploitation using the malloc and free gadgets. So now that we know it's heap exploitation, you would probably start looking into different heap exploits and how the heap itself works. So here's a quick crash course on what the heap is. It's used to store long-lived dynamic memory, which is data of variable length, so length not known at compile time. For example, the length of the name of your lemonade stand. We don't know how many characters the user is going to enter. So that's variable length. And then we want it to last beyond the scope of one function call. So say you wanted to like return it the from a function, you would need to use the heap to store that data. Um, and different implementations of a dynamic allocator exist. And that's going to depend on what operating system and C library you're using. So Linux uses ptmalloc. Physical thread malloc is what that stands for. And that's a fork of dlmalloc, which is Doug Lee malloc, which is a very classic algorithm for heap bookkeeping. And the heap is the memory space managed by the dynamic allocator. And the heap functions through two main APIs that the program is going to call. Those functions are malloc given a size and free on a pointer that was returned by malloc. And allocation needs to be very fast. The allocator has to make a trade-off between catching security issues caused by different bugs, like misuse of these two functions, and performance. So it can catch more security issues, but it's going to take time to catch those issues, or it can be faster, but it might make exploitation easier for an attacker. So different glibc versions are going to contain different implementations of this dynamic allocator implementation, and those different implementations are going to make different trade-offs because the heap is always on this pendulum swing between one side being people being scared of security and wanting more checks, and the other side being people thinking the heap's too slow, and so we add more caching layers and eliminate some of those security checks. So what are some of the dangers of the heap that could lead to these type of security relevant bugs? So allocators use caching layers for speedups, but these can make exploitation easier. So a caching layer allows the heap implementation to do less work for an allocation or free by caching that. But the cache, it probably has less checks than the code that it's bypassing. And so the things that the program can do to cause some of these bugs are forgetting to free memory, which can lead to resource exhaustion. We normally call this a memory leak. And using or freeing memory, uh, using or freeing freed memory can corrupt the allocator's internal metadata because once you free a chunk, you're not supposed to use it anymore, and the allocator is free to store whatever it wants inside of that memory. And so if you're editing something inside of freed memory or reading from it, you could just be reading total garbage, the contents of another chunk, because it could have been reallocated and repurposed for something else. Or you could be editing the allocator's internal state and messing up its view of the world. And if you free a freed pointer, you're going to be asking the allocator to interpret a freed chunk as an in-use chunk. and it'll make certain assumptions that might be incorrect, and that could lead to some security issues. And I included a couple links if you want to learn more. Okay, so clearly the libc version is very relevant to what attacks are going to be possible and what constraints we're going to need to pass to enable those attacks, and also how we're going to exploit those vulnerabilities. So the way we check the libc version is we get that SHA-256 hash of the Docker image from the deployment bundle, and we're going to spin up an instance of this image as a new Docker container, and we include RM so that it doesn't stick around. And I gives us an interactive shell and T a TTY or terminal. And then once we drop into this shell, we can use LDD list dynamic dependencies, which is an internal command to the C library, and pass it the version flag, and that tells us we're running glibc 2.31. And this is Ubuntu 2004, and 2.3.1 is a pretty old libc version. This hasn't been the latest version since 2020 or earlier. So that's a pretty good hint that there are probably some vulnerabilities that will be easier for us to exploit. So the cache that is present in glibc 2.31 that's particularly relevant to the challenge is called the thread local cache, or tcache for short. And this is an optimization that is designed for small and repeated allocations on a single thread. And why this optimization is particularly important is because that's a very common behavior of programs. When you're using malloc, you're usually calling malloc, and then for the size, you're passing in the size of some struct that you use in your program. So some type that is important to the state of your program. And the size of that type, it's going to be constant. It's always going to be the same because the size of that struct is determined by the fields and data types within it. Uh, and you're probably going to be freeing instances of that struct and then trying to create new ones all the time. So what that means is you're allocating chunks of the same size, freeing those chunks, and potentially doing these in very tight loops. So a good optimization that could make the heap a lot faster is if when you free those chunks, you store them someplace, and then the next time you get a request for that exact same size, which is very likely to happen in your typical program, you can just return that chunk that you set aside instead of doing all the bookkeeping that would be required to actually allocate a completely new chunk. So how do we implement this? In glibc, can you go back? In glibc, they implement this by using a singly linked list. And so there's this area of memory internal to the heap allocator, like next to the heap, where they store like a bunch of slots for different bin sizes. And each of these slots, they have a count of how many chunks are in that bin, and then a singly linked list of the chunks in that bin. So if you think back to your basic CS courses, a singly linked list is a data structure where each element starts out with a pointer that points to the memory address of the next element in the list, or null if it's the last element. And you can traverse the list by just following those pointers one by one. And it's very, very fast to add elements to this list because you just kind of swap where the pointer's pointing to, substitute a new chunk in, and then wire that chunk onto wherever you want the next element to the list to be. So it's very, very fast to insert and remove chunks into this list. So that's good for us when we're freeing and allocating all the time and not really like traversing this list in a linear way. And so where do we store this linked list pointer? Well, the chunk is free, so that means that all of the memory inside of that chunk that normally would be for the user to store their data, the heap allocator can use that memory to store the pointer to the next element in the linked list. So this is very convenient for us because the data inside the chunk, that's precisely the memory region that we can control using those scanf calls. So the first 8 bytes, 8 bytes being 64 bits, which is the size of an address or a pointer on the AMD 64 architecture, which is what this challenge is for. Um, those first 8 bytes are going to store that pointer. And so on when we free a chunk, we're going to add it to the start of this linked list, and we can just keep adding chunks to the start and adding them to the start. And then when we later allocate uh, a chunk of that same size, we're going to scan through all of the bins in our Tcache and jump straight to the bin that matches that size, and then see if there's any elements in this linked list in this bin. And if there is, we can just take that chunk out of the linked list, point the head pointer to the next chunk, and then return that chunk to the user. And that's very fast. It's only a few pointer updates, and you kind of bypass the slow parts of the heap allocator. But this next pointer can be very easily corrupted by an attacker because writing to the content of the heap chunk, that's a very common operation that you're going to find in a lot of binaries. So it's a very easy target. And so in summary, the Tcache it's a very fast path on the heap. It bypasses the normal heap behavior, and it has very few of the security checks that would normally catch what we're trying to do, which in this case is get the heap allocator to return a pointer to wherever we want, to an address that's not actually in the heap. And so the normal heap path of code flow would have a check that kind of looks at that pointer and notices this doesn't look like a heap pointer at all. But the Tcache, it's just trying to go as fast as possible. So it doesn't look at that pointer. It just returns it straight back out. So the technique we're going to be using to exploit this is canonically known as a Tcache poison. And what this does is we create, we gain access to a chunk that has that next pointer, and then we write into that next pointer the whatever location we want the heap to return, and then we allocate a couple chunks to go down the linked list, return that chunk, and now we can have an arbitrary write over whatever address we want. So how does this work? So we first allocate two chunks of the same size. That's important so that they end up in the same bin. And then we free the chunks in order. And so, as I said before, because freeing prepends to the linked list is going to look like head points to B points to A because B was freed second and prepended in front of A. And then if we then write the next pointer, which is the first 8 bytes inside of that B chunk, and we write it to whatever address we want. Sometimes you might do -0x8. I'll explain why that's relevant later. But whatever value you write in, whatever pointer you write into B, now the list is going to look like head points to B points to arbitrary location. So all we have to do now is call malloc once. Now this will pop the first element out of the list, which is B. And then if we call malloc again, now the element at the top of the linked list will be that arbitrary location. So using these 4 actions, or sorry, 6 actions, malloc, malloc, free, free, malloc, malloc, and with that right in the middle, now we just gotten the heap allocator to return whatever address we want. So now that we have this primitive, how can we apply it to the lemonade stand challenge and exploit the and do those writes that we need to do to get the send flag command to work. So the second, it's not really important what this field is or what it does, but just know that there's another pointer or field that the dynamic allocator likes to store inside of that free chunk, and it's at the 8 bytes off from the start. So the first 8 bytes are the next pointer. The next 8 bytes, they just get set to 0 after this Tcache pointer, after this Tcache poison. So that can be important because like those bytes have to be writable or else you'll crash. So it can't just be any value that you want to return from the heap allocator. It has to be valid memory that you can write to so that it can null out these 8 bytes. But it does set them to 0, so that can be useful for us for setting that mode value to 0. And we can control this by just allocating at 8 bytes lower in address space than the mode variable, so that when it allocates 8 bytes forward, it's writing directly to that mode. And so that's why I say we poison mode minus 0x8. And that's the same minus 0x8 as in the previous slide. Um, and then we poison the debug control password field, which is in this challenge, it's 266 bytes ahead of the G debug control symbol. And then once we've gotten that arbitrary location to be one of our stand names, we can rename that stand so as to set the password to be something that we know, and then we can call send flag. So if we put that together into a Python script, next slide, we can I'm using Pwn tools here, which is a Python library commonly used for exploit development. We can define this Tcache poison function. It has those same function calls as was on that one slide explaining it, and I use that size variable so that they're all the same size. And malloc and free and scanf, these are all functions that I've defined that just call the relevant commands, which are stand create, stand delete, and stand rename, respectively. They're just convenience functions to run those commands. And then I define a couple of constant variables, those hex numbers at the top, those are the addresses that we want to write to. They all start with that 0x40, which is that base address that we saw at the beginning with checksec. And it's always going to be those values because there's no pi. And so we poison those two addresses. In the second case, we write a known value, which is 4A's, 4B's, 4C's into that secret address. And then because I'm doing that minus 0x8, the A's and B's get skipped. The first 8 letters get skipped. And then just the C's get written to the password. So then we can call send flag with the 4C's. And that will pass the mode check because the Tcache poison set mode to 0, that first Tcache poison. And then the second Tcache poison set the password. And so both of those checks will pass and it should send us the flag. So once we've developed this script in Python, you can test it by running the binary locally. In order to do that, you can either develop your script inside of the Docker container, or you can copy out the libraries, which are libc, libm, and then the dynamic linker, which is ld. If you copy all those out and use a tool called pwninit or something similar by patching the binary, you'll be able to run it locally. And then you can test your script against that, open it in a debugger, everything you need to do to figure this out. And then once you get it working, you can run it against the server. So in order to do that, you need to convert all of the commands from just directly sending them into a process to sending them as WebSocket commands to the WebSocket server. And I did this by porting my exploit to JavaScript and copying and pasting it into the console on the website. You can also use a WebSocket library in Python. Either way works. Any other programming language works. You just have to send the data over the WebSocket. Make sure you're not sending it too fast so that it's listening at the right time. And then since the addresses are constant and you're not doing any calculations based off any data the server sends you back or anything like that, you can do this exploit completely deaf. You can just send a specific sequence of bytes to the server that are constant. It'll work every time, get you the flag every time. But if you want an additional challenge that is not constant, you can try and leak the libc address. Libc, since it's a dynamic library that's imported, it's not going to have that constant base address. So if you manage to leak the libc address, you can call some functions in libc like opening a shell, and that's an additional challenge, popping a shell on the server. I know someone in Discord managed to do that, so can check that out. And that should be it for Lemonade Stand. Thank you.
Yeah, thank you really much, Spencer, Adam, and Evan, for explaining those puzzles. So now we're going to move on to ROM hack, which was the least solved puzzle. And the creator of ROM hack couldn't make this meeting, but we have a walkthrough by him that is both linked in the slideshow, and we're going to play it as well. But first, here's like a slight description of the puzzle. So ROM hack is a reverse engineering challenge, and it relies on using the decompilation of Pokemon Emerald. The repository is linked here. And yeah, here's the clue and here's the UI. Okay, so how the basics, the video is gonna go more in depth about this, but here are just some like basics. So you wanna look through like the repo and like use it, and you wanna discover the script while looking through like the code, flag checker script. And if you write something that like decrypts what this is, what the script says, you discover like what settings you need. When you actually play the game, you discover like you need like to be male, and have Mudkip and be named Tim. And also there's a function called did player input mystery event that Kosi edited a lot. He edited this, and like if you list out all the constraints and convert it to words, the process is a lot more complicated. This is just like a general overview, by the way. You get a password, it says all your secret base belongs to. So this is what you get by like decompiling like the code and looking through it. And then if you actually follow the instructions that we put in the web page and then like set everything up, um, this is what you have to do in the game. So you have to use the ROM hack patch with this GBA and patch it with romhack.ips. And here are the requirements that you should like discover from looking through the decompiled repo. And if you like choose the right character setting, and if you go to the Pokemon Center, there's like a new NPC there. A submit password screen should pop up. And then from the last slide, you should get like the password is all your secret base belongs to. And if you submit that, you should get the hash. You should get like something like the flag, I mean. And yeah. So here's the walkthrough video. Let me just play this. It's gonna be 15 minutes long, so if you guys are like watching this video, well, I recommend watching this, but feel free to like fast forward or something. Yeah, this is the old UI, by the way, but right now it looks a little bit different if you guys visit ROM hack. I'm sorry. He's just setting things up right now. So basically, once he finishes building, yeah, he can apply the patch. Oh, this ROM hack patcher is also linked in our slideshow, by the way. So here he's explaining the requirements, by the way, and I put these in the slideshow. Yeah, so basically, this is the Pokemon Center, which was hinted at. And if you visit this town, you should see this NPC, and this will be the password thing I described. Here. There's this new person, and then yeah, if you have the right settings, like male Tim Mudkip, which you saw Kosi do earlier, you'll see the screen. And so here's the hash, prepare for trouble, make it double. Yeah, Pokemon reference, we love it. And you would submit this in the command center. This is actually like one of the, well, it's the only puzzle that doesn't have like a unique hash due to it being harder, just to like put into the game style. But yeah, we appreciate that like you guys didn't spread this around. Yeah, so now we're looking for the new code that he added. And yeah, this is a lot to do. So honestly, congrats to everyone who looked through this and solved the puzzle. Because as you can see, there's like a lot. So he goes to the flag checker script that I mentioned, and yeah, this is like how you determine like the character settings. Okay, so this is the did player input mystery event. Right, so this is the constraints that I referred to in the slideshow. Um, Basically, if you decode these, it's gonna give you the password, which and yeah, they're all in like this format. Okay, thank you guys for staying with us and watching that very long video. I know it's long, but it's very informative. And yeah, he basically made that walkthrough because he couldn't make it. But overall, ROM Hack is like a very cool game, and as a Pokemon fan, I think it's like honestly worth it to just like play through it, even if it's sold now, because it's very cool. Yeah, okay. Here are just a few shout outs. So here are our first bloods. Listed here, shout out to everyone who solved these puzzles first. And special shout out to Sam Volta for solving the chest before bug fix and being the only one to do so. Here is our leaderboard, and yeah, basically just shout out to our leaderboard. Um, Very good job, guys. Also, just shout out to everyone for like trying the puzzles, because even trying them is like really cool. And we really appreciate it because we put in a lot of work into the puzzles. Uh, yeah, just a reminder, just like if you have any questions, ask in the chat or like if you guys are watching this video after the live is ended, just like ask in the Discord and we will be glad to answer any questions. Yeah.
And we'll edit the slides to add a link to a GitHub repo that has the source code and any supplementary scripts that each of the puzzle authors created when they're making the puzzle.
Yeah. Thank you, Spencer, for mentioning that. We will be sending that out along with the slides. We'll let you guys know when everything is done. We'll send it in the announcements channel. So yeah, thank you guys for coming to the live and congrats to the top 50 and everyone who solved the puzzle. Okay.